Welcome back to our PCB layout-driven design with VSS series here on AWR TV. In the previous step, we looked at component modeling. Now we're going to move on to the actual ideal PCB design. In this step, we're actually going to accomplish two steps. The first step is sort of a leftover piece from step one. When we were talking about the component modeling, we touched very briefly on including the pad stacks for the PA. In other words, a small piece of layout that really is very much related to the component modeling because it's essential for that bit of layout to get done to allow us to put the component on the board. So we'll just take a brief look at that in a little bit more detail than we did in the last video. And then we'll move on to looking at assembling the ideal PCB. We're going to use the components only, except for where we have the pad stacks incorporated into our component model. We won't look at any interconnects. What we'll do is we'll do some simulation in Microwave Office to assure ourselves that the models are accurate and they're giving us a reasonable answer for things like gain and P in versus P out. And then we'll go ahead and take that ideal board and put it into VSS and look at EVM, but we're going to do that in a very special way. So here's our ideal board design in Microwave Office. As you can see, there's a transmit receive chip over here, but really the details of our design are over here that we want to focus on, where we have some balance and our power amplifier chip, a TR switch and a diversity switch as well. If we go into our PA package design, here's the behavioral model that we looked at previously for the package, for the power amplifier, where we have a nonlinear element to give us the P and P out characteristics. We have a low pass filter to give us the frequency characteristics, and we've used an HB tuner to give us the output impedance characteristics. I've also included two M3 sealant models, and the M3 sealant model is something that we want to use for three coupled lines put together. Now the sizes and dimensions I've chosen for my three coupled lines here, you can see it's rather small, 0.4 millimeter spacing, 0.4 millimeter width, and 0.4 millimeter length. I've chosen that because that's going to be the size of my pad stacks. And where I have coupled lines in my pads that I'm very concerned about, like on the input of the chip here and on the output of the chip here, with these pads going to ground, I want to be able to incorporate that into my design in a very immediate way. I want to incorporate it very early in my design process because I know it's going to be a factor in my design. Well, now I could take all of these chips, my splitter, which represents the signal coming out of my transceiver, my balun coming out of my transceiver into my power amplifier, the TR switch, and an antenna balun, and I can cascade these together in VSS. Now each one of these models individually comes from Microwave Office with the exception of the splitter, and I'm just using that to split my signal here in VSS. But as a LinS block, I'm modeling my balun. So this is taking the S parameters from Microwave Office and representing them as a linear simulation-based block. My PA design is being modeled in Microwave Office with that the microstrip coupled lines, as well as the nonlinear elements that and the detailed elements that we showed in the PA package model, but it's being brought into VSS as a nonlinear simulation-based block. And similarly, the TR switch and our antenna balun are LinS blocks as well. And so what this is doing is it's reusing the models and the simulation in Microwave Office, and on the fly or immediately as we need it in VSS, it generates the appropriate model in VSS for us to use. When we model our entire board, again, that's this schematic here. We model that in Microwave Office. Our P in, P out curves for our PA looks something like this, and our ideal board is somewhat less than that. We've lost some power out versus power in, and that's mainly because of the mismatch in these circuits as we're cascading them, as well as the insertion loss for the various components. If we look at the gain, we see a similar thing where we've lost an incredible amount of gain because of the insertion loss, which is on the order of 4 or 5 dB, but the rest of this loss that we're experiencing is due to mismatch. Now we can take our WiMAX system for the transmit side, and instead of our amplifier under test, we insert that entire board subcircuit that we developed in VSS. Again, that's That's this circuit over here, reusing the models from Microwave Office. We embed that as a subcircuit in VSS, and when we do the simulation, the EVM simulation that we've been looking at, you can see that we've degraded quite a bit from where the PA alone was. The PA alone was giving us roughly 24 to 25 dBm P out at 2.5% EVM, and you can see that we don't even get to 24, 25 dBm out at 8% EVM, so we've degraded the system quite a bit. A portion of this is due to the mismatch, but the vast majority of this is due to the mismatch. And so what we're going to look at as we go forward in the rest of our design is how can we better use the interconnects, how can we include the interconnects into our design so that we can maximize our EVM. In other words, reduce it down quite a bit to 2.5% at 24, 25 dBm. Can we do that given our interconnects making up for the mismatch that our ideal components are experiencing from package to package? Well, that's it for this installment of VSS for PCB design. If you have more questions about VSS, there's plenty of information on the website. There's examples that come with the free download of the product, the free demonstration download. There's white papers. There's additional AWR TV videos for both VSS and PCB design. And if you have any other questions, please contact your AWR sales professional.